Today we're going to talk about object-oriented programming some more, and then get into like some of the first new pieces of stuff that is CSCI 41 specific, like about data structures in general. I'm excited. More oop, less oof is my slogan for the day. I guess I first want to just ask you this question. I do this in my 40 class as well, but I know a lot of us are new to the terminal. Is it going okay? Do yell at me, ask all the questions you need to. We'll get you helped out, but this is just a funny picture because I recommend Vim on the terminal, but a lot of the cool kids, once you get out of this class and you learn things for yourself, everybody likes to use Visual Studio Code as a graphical editor. I can help you install that one day, as long as you prove to me that you've learned Vim properly, because I need to teach that too, all right? So that's a thing. And then once you get so happy with Vim, the funny thing is a lot of people like to install like a Vim mode in Visual Studio Code because they miss it so much. I do that. So look forward to that one day potentially. All right. So yeah, the first thing I want to talk about is something that is specific to your Lab 0. I remember those tests, they were involving those things called string streams, and they were a little weird. Maybe you never heard about those before. Well, let me at least show them to you once so that you can make those tests and understand the ones that I already wrote for you. Okay, so the standard way to look up something in the standard library is to go to the documentation page. There's a couple websites, two competing ones. I like one, other people like others. Let's go look at the documentation for that for this header, S-stream, and we'll see what lives there. So docs, short for documentation. And so it's just this C++.com website that I love. It's got all these things. You can search for C++, whatever you want, S-stream if you're not there already. And usually it's just the first link to that header. It'll look like this for you, but I prefer it like this. And you can click on all these different things that live here. There's a bunch of different types, classes that live within this header file, but we'll talk about string stream. And it comes from a long line of things. Remember that the type of cout is like an O stream, something like that. So there's like some hierarchy here that you'll eventually read about, maybe one day. This is like a section of a CSCI 40 textbook. If you still have your CSCI 40 textbook, there's a section on inheritance, and that's what's going on here. But yeah, string stream like gets powers from cout-like things and cin-like things. It's interesting. And here's like the stuff that you can do to it. It's got a constructor, of course. It's got a stir method. You can put stuff, you can get stuff out of it like cin. It's got that operator. You can put stuff into it like cout. It's got that operator, which is kind of cool. And then there's plenty of other things that you can pretend that it's a file as well. It's like your own personal cin/cout. That's how I like to explain it. But usually, if you're like confused about any of this, probably the best place to click is like the constructor, and you scroll down. There's always like some sample code. It's like, oh, make a string stream, put some numbers in a space between the numbers in there. Oh, I can extract those things that I put into it. Interesting. Stuff like that. And you click on stuff. That's the way that I recommend to learn about things. But let's do that, and let me write it in code and comment it up. And this will help you for your lab. String streams.cpp, but it lives in a header file called S-stream because they didn't want to type it all out, I guess. S-stream. Right? That gives us access to string stream, so I have this type now. String stream. I can make an object of that type. Oops. Why does it always do that? There we go. String stream. And I'll give it a name. I'll call it SS. Why not? And the second I do that, it exists and it's blank. Right? It's empty, just like an empty vector. It's keeping track of a string secretly. All right. So you can put stuff inside the string stream, pretending that it's like cout. All right. Pretending it's cout or like a file, something like that. All right. That's the idea. So that's what you can do. And so you can use this kind of operator on it. It's like instead of cout, give it stuff. It's SS, give it whatever. Anything that you could have an output operator for, right? So give it 42 in a space. Give it the string blah. I can take anything that you could have printed to cout or put inside of a file. Give it, I don't know, 3.14 and a new line. So essentially what has happened once I've run all these things is it's building up a string secretly. So SS right now You can get what's inside of it. You can get the string that you've built up so far with this .stir method. You can also use that to set stuff, but it's like, if you call it, it will give you back, it's like this, it's const. If you call it, it will give you back the string that you've built up, a copy of that. All right, so that is useful. So ss.stir right now, if I were to call that, that would result in a string containing everything I put in here. So it's 42 space blah space 3.14, the characters. It's put in into string form and then a new line. Does that make a little bit of sense? That's what's going on. So that's kind of neat. String streams used to be the way to convert like numbers into strings, like to do that kind of conversion. That used to be the only way you could do it in C++. There's other functions for that now, but that's one way to do it. Interesting. That's kind of cool. And then you can also do the flip side of that. You can extract. You can convert strings to integers by putting it in the string and then getting it out. So just like this example was saying, once you've put stuff in, you can get it right back out and convert it away from strings. Like get the ins out again. Like parse that. That's the word for it. So let's do that. So you can extract that. That other operator also exists. You can extract from the string that you've built, which is kind of cool. So like if the very first thing in it was an int, pretend it's like a file that you're reading from, int x, or somebody's typing that exact string on the keyboard for you now. Like get out of ss into x. Cool. So that will take the 42 out. Yeah. And if I print it, see out 42. See out x, which will be 42. Let me show that. Ah. There it is. So that's my 42. It got it out. It converted it. It was in string form. Now it got it into int form as well. So that's an interesting idea. So it's a way to convert types, if nothing else. But it's really just a string at the end of the day. It's building up a string when you give stuff to string streams. But like the output operator works, and so that's how we're using it in the lab to test. Like, did the output operator put the right string into where it should have been? Like if I were to use it with a file or to use it with cout, would it have done the right thing? So you can always get the full thing with this .stir method to get the entire built up string with .stir. That's always a possibility, an option. So let's print that result. ss.stir, print it all out. I don't need an extra new line because I already put a new line in that string. And there it is. I've got 42 space blah space 3.14, and I broke the line properly. My terminal prompt is on the next line. Cool. Does that make enough sense? Questions about that?
Is there a way to output it backwards?
Just like the 4 first, then the 1, like go with the characters in reverse order?
Or like 3.14 down block and 42.
I see. So you'd like to extract the stuff in reverse order.
Yeah.
Yeah. So there's a way to like move around through the file. You will have to, you kind of want to pretend that this is a file is my recommendation.
Okay.
And the things that you can do to files are iStream stuff. You're reading from files, like ifstream is part of that. What can we do to a file? We can, I think, seek to a different place. So like the place that you are in a file is always like an index into where you are in that file, if that makes sense. It's like a file is just a really big long string.
Yeah.
And so this kind of like seek G method would say, hey, go to index 42 or something, like jump way over there. Yeah, you could do it that way.
Okay.
That's one way. But you have to like find where is the start of that thing now. Like you have to go back, where's the space right before it or something. So there's some work to be done. But worst case scenario, you can just like get the string out, reverse it, something like that. Yeah, that's a good question. Does that make enough sense?
Yeah.
Yeah. Other questions? All right. So yeah, this is just like your own personal cin, cout file, whatever you want to think of it as, but it's secretly just a string. That's what's going on inside of it. All right. Where are my notes? If we're good with that, now you can do your lab fully. I would like to talk about a type that we should know. Arrays. We love arrays. Arrays like give rise to vectors. We'll talk about that. But let's just talk about this most primitive thing. An array is just something with one name that can hold a bunch of stuff at once. All right. So array, a variable with one name, if you would look it up in a book or something. A variable with one name that holds a list of data items of the same type, each being directly accessible. And so we know these words, right? Every piece of an array is called an element. You can get to it with the bracket operator. That's a thing, which is like the .at for vectors, but you have more power, therefore more responsibility. But like if you were to say this, right, int r brackets 50, what does that do, right? It's going to make an array called r in memory, and it's just a bunch of boxes in order. You got 50 indices, which means you can access index 0, put an int there. It's 50 ints, right? You got to say the type of things. You can put index 1, index 2. You can put whatever you want, wherever you want it. And you get all the way up to... What's the last index in an array of size 50?
49.
Good. We're going up to 49. So I got to remember that. Array 50 is not actually there. All right? It's not part of you. So... yeah, you can get to anywhere you want with these brackets. You say, like, I want to set index 2, like r of 2, set it to 42, something like that. You can put that right there. That's how that would work. And just remember to not go past the end. You are allowed to go past the end with arrays, though. You can try to do this, but you're going to get garbage or your program will crash. Something like that. One of those options. Okay? So do you remember that? And yeah, I just want to show you some array stuff, just to remind ourselves what's going on. But this is, I think, self-explanatory enough. I don't have to go to code for that. Yeah, so arrays, just like vectors. If we remember vectors better, probably. But you have to use these brackets to get to a place rather than the .at. The .at does not exist for arrays. It's a more primitive thing, we say. Primitive type. Yeah. Questions about arrays? Is it coming back to us? So let's see. Now we need to talk about places where memory gets made. Because if I say this, it's not the full story, right? I'm saying like, okay, somewhere in memory this is getting made, but I need to be more specific in this class. So, okay, let's talk about the stack, all right? So the stack is where local variables get made. Hopefully we've remembered these words once upon a time. I would like to draw a bunch of stack diagrams now. So, just one. And then we'll pretend everything is living there. So when you make your array inside of a function, like inside of the main function, inside of some other function, what will happen is that array lives as part of memory for that function call. So like if you make something in main, that is called a local variable. Okay, there's global variables too that exist outside of any function. Maybe we've seen those before. But if I were to say this, int r, let me close off my a's here, size 50, and then I do stuff to it, like r0, make it hold 1 or something. What's going on is like that memory for r is part of main, in a sense. It's local memory to the main function call, which is the function call that exists for the life of your program, because that's the first one. But there could be other functions in your program. There could be like a foo function that does its other stuff. So let me write like a foo function really quick. So here's a foo function. Let's say that foo also makes some memory. It's like it's got its own array also called r. That's okay. They're different places. So whenever foo gets called, it's going to make some memory on the stack for itself, in its own little piece of the stack. All right. And when I say stack, I mean the function call stack. That's another longer word for that. So this is the kind of diagram I want us to recall. So here, when the program begins, somebody, like the terminal, is calling main for us. All right? So main starts its life, and that's the first piece of information that's pushed onto the stack, we say. So like here's a stack of papers, main, do your job. So I'll label that. So this is called main stack frame. All right, so this is a place in memory that remembers like what main is set out to do. It's going to store all of main's memory and also remember like who to come back to. So like main eventually returns to the terminal. It needs to like know where that is. Like that's kept somewhere as well. It's like who you return to is also saved. But yeah, all the memory that is associated with main lives in main stack frame. So if main makes an array called r, I can't write a proper A today, sorry. Then it's going to go here. That's where I should have been drawing it, really. Okay? R lives here. And that's this one. and R of 0 is set to 1 or something. There. That's how that happens. That's main's memory being touched. And if main calls foo, the way this works right on the stack is we add a new stack frame to remember that, all right, now we're in foo. We're working on foo stuff. Foo has its own local memory eventually. We also need to remember that like the person below me is who I return back to. That's how that's saved as well. So that's kind of cool. And foo makes a memory, local memory to itself called R. And there's no ambiguity. It's a completely different place in memory. So 1, 2, 3. That's foo's R. Okay, and then eventually foo returns and we come back to main. So foo knows like the person below me on the stack is who I need to come back to. So like there's addresses being saved, stuff like that. And then essentially this goes away. I should be erasing it, but I'll draw a slash to it, through it, to mean that like we came back to here to main, and now all of foo's memory is gone. Because think about it. Say that you call foo once every like time you iterate through a loop. If you didn't get rid of all those stack frames, you'd eventually run out of memory. So it's like only the current things that are being called are on the stack. Anything that has returned, all that memory gets reclaimed. Okay? So those are words I want you to remember. Are there any questions about that? I hope we've heard that before, right? That's important. That's 40 stuff. So that's how functions get called and they return. And so local memory, arrays are just local memory. It's just wider. Okay? That's that. And now here's some cool, potentially new stuff. All right, so arrays, they are secretly pointers, which is disgusting, but it's going to be nice, I promise, for a few different reasons. So if I were to say this, int r equals 1, 2, 3, dun. Really, I've been drawing it like this, right? It's called r, it holds 1, 2, 3. But secretly, every array is a pointer to its first element, so I shouldn't be drawing it like this. Now we can know the secret. So R is really, if I were to say R, it's really a pointer to wherever the start of that array is. So let's say these are addresses. This is like address 100, this is 104, 108. These are ints. They do have to be right next to each other. So then that would mean that R itself, just by itself, the name R, it will hold the address 100. It's a pointer to right there, okay? And the second that's allowable, and that is a thing, you can start making pointers into your array again. You can say int star p equals r, and that's fine, because what is r but an address? It's just a number, like 100. So that would make p also point to it. It will hold the same thing, 100, and boop, also point right there. Which means if I were to dereference p, I'd now get 1. Does that make sense? That's what would happen. So let me prove that to you. That's kind of weird. Now I can make actual arrays in code. So int r equals 1, 2, 3. I claim that if I were to print just r by itself, then I'm getting an address. The address of the first element in r. All right. So another way to get at that address, right, is to say, give me the address of operator. Give me the address of r of 0. Yeah. So if what I've said is correct, these are equivalent ideas. R is a pointer to its first element. Here's the normal way for us right now to think about getting an address of the first element. So those should print the same thing twice. And they do. Look, that's the address apparently where the 1 is. If I rerun it, of course, it gets loaded into a different place in memory. So it's a different address each time, but it's working. They are the same place, just R by itself, which is kind of cool. It's pointing to that 1. Which means, right, star R is going to print 1, isn't it? It's a pointer to the first thing. That is a way of printing 1. It's a way of getting that 1 out. Potentially messing with it, like star R equals 42. That's a thing, okay? So to come full circle, now I need to say that because you can do this, this kind of syntax is really just shorthand for pointer stuff. It's shorthand for pointer arithmetic and dereferencing. So R of 1, just like R of 0, if I were to say star R, that gives me, that goes in here and gives me the actual 1 out. I can compute the address of the next thing based on the starting location of that array. So R of 1, it's really doing this. It's compiling into this. It's doing R plus 1. I cannot write ARR today, guys. R plus 1, and then dereferencing that. So this shorthand with these brackets is really just doing exactly this, bless you. So isn't that great? That's exciting. So first of all, if R of 1 gives me this 2, R plus 1 is not actually calculating address 101, is it? Because that would be like in between the 1 and the 2. That would be weird. So pointer arithmetic is nice to us. If this R is an array, or if it's an array of ints, that means R by itself is a pointer to an int. And if I'm going to add a 1 to a pointer to an int, it knows to go 1 int later, not 1 byte later in memory addresses, which is nice. And so it's really going to calculate, R plus 1 calculates the address 104, okay? Calculates the address 104, and then it dereferences that, and it gives me the 2, all right? That's what's going on. It's calculating that different address. Really, this syntax is getting compiled into this. There is no difference at all. Deep down. You can double check that when you get to CSCI 45. So here, if I were to say R plus 1 and dereference it, that is exactly equivalent to R of 1. That will give me that 2 out. That's what's in there. And you can, of course, use that to set it as well. So there it is. Is happy. Questions about that? Does it make enough sense? It's weird. It's weird, but it's useful. All right. How would I use what?
Why would you use one of the other?
Oh, you wouldn't. This is kind of disgusting to want to do it this way. I'm just trying to teach you what's going on under the hood. Yeah, you would always want to do it the normal way, I would say. But there are algorithms where it would make sense in a loop. If you go read the standard library, you'll see stuff like this. They like set a pointer equal to the start of the array this way, and like inside of a loop somewhere, they're saying stuff like star p, like advance, like increment the value there, and then also increment the pointer to get me to the next thing in the loop. So that actually sometimes looks cleaner than to do it this way with like indices and things, because like it's easier to know when you're done. But like that's a way to like increment the thing underlying that the pointer is pointing to, and then also get to the next int in the array. People have their preferences. But yeah, that's a good question. But usually, at least in this class, it makes more sense to use it this way. But now you know the secrets. Yeah. I guess the real reason I'm trying to teach this to you is because you can make these kind of things. You can say int star p equals r, and this is just a pointer to one place in memory. You can say p, like star p gives you the 1, but you can also do this, just like you can say now that I've made p, just like I can say r of 2, because r by itself is really just a pointer to the start of the array, I can say p of 2, even though p is just an int star. It doesn't even know that it's an array, but you can treat it like one. That's the secret. That's what you can do now with this knowledge. Because really, this is, this translates into, all right, p plus 2, dereference all that. And that'll check out. That will work as long as there is an array deep down there. As long as you can get to that address, really. You can make a pointer to a piece of your array, to the start of it, potentially, or somewhere in the middle, and start using that thing, that pointer, that one pointer, not just to a pointer to that one thing, but you can go further down. You can treat it like an array. You can use that syntax because you know what it's going to compile to. All right, that's the full story. Does that idea make sense? That's pretty cool. And so now you have options, right? If you make a sum function, like you can pass the array that looks like this. You got to pass the size. They don't know their size. You can also have done it like this. And you could have had the exact same implementation because these two types are equivalent. What is an array but a pointer to its starting address? Interesting. All right, so I think that's honestly all the code that I want to write today. The rest of today is going to be a bunch of diagrams and me drawing stuff, and that's most of what CSCI 41 is going to be for you. I'm going to draw pictures, pretty pictures, as pretty as I can make them, and you're going to implement those pictures. All right, that's what I want to get you good at. That's how we learn things in this class, particularly. All right, so yeah, the other magical thing that we now obtain is we can make arrays on the heap and understand why it's okay to like save it as an int star if it's an int array. So let's talk about this. So there are, of course, two magical places, a couple magical places of memory. You got your stack. It's growing as functions get called. You've got global memory as well, if you remember that. You make something outside of like anything. And then you also have the heap, which is a magical place where like you can build things shiny and new as you want them. Okay, so that's a secret second place. So I'm going to draw these pictures with that in mind. Like we're in a function somewhere, so we've got local memory on the stack, And then also the heap is a place where we can make stuff dynamically, okay? So to make a single int on the heap, you say new, right? New int. Give me an int, please, on the heap. And the way that this runs is like it makes it and then it sets it in its address. You get back the address of that thing that got made for you. So new int on the heap does this. It makes a box that holds an int, capable of holding one int, shiny and new. We just made that. And everything on the heap does not have a name. It only has an address. It's like 100 is, let's say, the address of this new int that got made to us. And so the 100 is what this assignment statement is seeing, and it's shoving that into an int pointer called I. So I gets to hold that 100, and that's our window into this place on the heap. That's how we can get access to it, okay? And we could use that to set the value, of course, like star I equals 42 or something. And then once we're done, once we're done with that thing on the heap, that one int that we made, shiny and new, we can delete it. Pass it around between functions as long as it's still there somewhere. But the second you say delete, then this memory is going away. You should not be using I anymore because that address has now been reclaimed. Okay, so that's undefined behavior now. So there's that. You can use that same syntax, right, for making an array of ints on the heap. So you say new int, not just new int, but new int bracket stuff. So you'll say that if I were to say that, new int brackets 3, that's going to make space for 3 ints contiguously in memory. So an array of 3 ints on the heap. And we're always getting back the starting address of that thing. That's what new gives us back. It's always going to give us the starting address of that array of ints. So let's say that lives at 104, 108, 112 for those 3 values. So the starting address then of this array is 104. Again, it's shiny and new. Beautiful. And we're getting back the starting address of that. If it's an array of ints, that's an int star. If it's an array of ints, that's an int star. So we're going to store it like this. You're forced to use this kind of type. But that's okay, because now we know we can use the array-like syntax on a pointer to an int as long as it really is an array deep down. That's pointing to here. And you can mess with, like, you can say r of 0 now. You can use that syntax even though it's just an int star, because it really is secretly an array. You can say r of 0 equals 42. Like, you can set that right there. Otherwise, it's garbage, right? At the very start of time, it's always garbage. But I can say r of 0 equals 42 now. 42 is what it's holding. That's not legible, is it? 42 is what it's holding now. And then, ta-da, we can use it, okay? And the second you say delete, it's going to go away. But now we have to be very specific because C++ doesn't know any better. Because we have made both an array of ints and a single int on the heap by saving it as the same type, delete is not smart enough to know which kind of thing we just made on the heap. So if I were to say just delete r without these brackets, it would just go and delete this very first int. Because it doesn't know, like that was not an array. I don't know, it's just, do I go there and see one int or do I go there and see multiple ints? Like it doesn't know if this syntax works yet. So you tell it. If you make an array on the heap, you just got to use, you say delete bracket bracket, not just single delete. And that goes and that deletes everything that got made starting at that address on until the end of whatever that memory that you made was. Okay, so that's the secret there. Just got to be bracket bracket with the delete to get rid of the whole array that you made. All right, but again, you're referencing it using a pointer to its beginning because that's all that new gives back to you. It's always you're getting the address of where that thing lives in memory, then you go use it how you wanted to. All right, now any questions about that? You see it? Somehow, slowly but surely. All right, so now here's my question for you. So this is a complicated question. You do not have to get it right, but I want you to think about it and have your brain hurt for a while. That's how we learn. All right, so I want you to maybe, well, first of all, of course, I want you to get into groups and say hi, talk about your weekend if you want. Introduce yourself if you're sitting next to somebody that you haven't seen yet. And then also, after all that, of course, please, we've got some code here. I've made some code. I'd like you to draw, like open up Paint if you need to, or like use the paper that you got out in front of you. But I'd like you to draw what memory looks like in this style, all right? With X's when things go away. I'd like you to use this style. So like we've got stack stuff, local variables, and we've got heap stuff. Boop. Dynamically allocated things. I'd like you to draw what would happen if I were to run these 3 lines of code. All right, so that's your step 1. So please do that as a group. Convince your neighbors that you're doing it right. So draw what memory looks like after these 3 lines have run. Taking care to like separate the stack and the heap. Some things are on the stack, some things are on the heap. And then Also, draw what's going to happen when delete P. If I were to say just delete P, when that goes away, what is going to be, like, what's going to have the X's drawn through it? So, like, draw an X to mark what's going to be deleted. Yeah. So that's the setup. That's what I want you to think about right now. I can give you this slide in a very small way. Come up and take a picture if you need to, or take out your binoculars. Use the zoom on your phone camera. But there's that, if you need it. Try to draw. Are there questions about the question? All right, go forth. Try it. This is a hard question, but it's going to teach us what we know and what we don't know. So I'll give you plenty of time. I'll give you a few minutes to try this. You don't have to write the answer anywhere but for yourselves. What will memory look like? Those are weird looking types too, aren't they?
I apologize for being late.
Those are
I
right.
apologize for being late. The Expedition 33 soundtrack's so good that I ended up missing the bus stop.
The attendance is still going if you can do that within the next couple minutes.
Okay, thank you very much. Also, these are back my numbers, so. What's going on, Randy? So, what's new today?
You'll have to wait and listen. I'm not going to give you a breakdown. That's too much. Question, yeah.
What does the double asterisk mean?
That's another type. It's an int star star. So it's a pointer to an int.
Oh, okay.
Yeah.
Oh,
But it's still just one. It's still one thing, just a type of thing that you could hold. I could hold an int star star. That's one entity. But it holding the address of an int pointer, I guess. I don't know you can read it. Because like an int star is a pointer to an int, it's holding the address of an int. And then star star is then a pointer to an int star. A single star pointer. It's like it's holding the address of an int. Yeah.
I was trying I can't I can think like a couple times because I stuck read only even though I chose missions 2077 from like models.
Show me the error.
Like when I try to write read only.
Did you try to use Visual Studio or anything?
I think I double clicked it in my thoughts for it. And, you know,
Visual Studio. Did you try to connect to the server in Visual Studio?
oh no, I didn't.
The error should only happen if you like do something more contact.
Oh, yeah.
Get out of here. Oh. All of that stuff is not blue, but that is you, right?
Yeah.
Okay, yeah, I thought you decided like something very odd. Like, any who owns all of your files to the administrator's account, which of course you don't have access to. I don't think you should. I have to do this. I have to fix it.
Oh.
So that's the big. Did that happen during the entire novel or something weird? I think so. Wait a second. Where are we?
This is my.
This is your own computer.
This is my.
Oh, okay. So you're. Okay, I can fix that. Right here. I was very good at this. Yeah, server. No. Sorry. That's not your username. Somehow your host, which lives in your home folder got owned by your home folder is owned by you, but the contents for some weird reason is now school folder. Wait, now it's back. now change.
Oh no, this is the different file. This is the actual lab series. Lab series.
So it's in the lab.
Yeah, lab series.
Right, okay, so it's the lab's folder. So what we want to do is change who owns this. Let ch own. Change the owner of this directory. Dash r. And then we want to change it to your username. Yeah. And then that's the owner, and then also the group who owns it. Doesn't really matter, but that's also the username. And then you give the directory names. And because it's currently owned by that's a secret operation. So you gotta type your root password, but never again.
No, I don't understand that because it's like the third time I uninstalled and reinstalled it. I went to Doug in and I changed all the permissions in the files and that shit just gave me let me add it. So
What? This is only faster.
yeah, this is
You shouldn't need to change any permissions. See, show me during lab tech how you did it. Right? We'll try to figure it out. But at least you can add this to the project. Alright, I think that's enough time. That's how much I wanted to give us. Are there any questions that came up as we were doing it? First of all, so I'll show you the answer. Show you how we think about it. But let's take a look. Can any brave soul tell me how many boxes total are going to get drawn somewhere? Okay, I see one guess, one idea. Any numbers? Thinking 4, we're thinking 3, 4. All right. Any other thoughts?
I want to say 42.
You say 42. Nice. All right, so let's find that out. And then also, how many on the stack versus how many on the heap? I guess, how many on the stack then? Thinking 1. We agree 1, maybe? All right. Let me show you how I think about this. This will be very educational. All right. So, okay. These lines, they do something. When you make anything with a name, unless it's outside of something, it's like a global thing. Anything with a name lives on the stack. Stuff on heaps do not have names. They only have addresses. That's all new gives you. So anytime you see a name, definitely that thing is living on the stack. Okay? So there's only going to be one thing. It's P. P is going to get made and live on the stack there. And it's going to hold the address of something weird. So you can read int star as, just like you can read int star, right, as a pointer to an int. It's capable of holding the address of one int. You can read int star, the type, as it's a pointer to an int star. It's a box capable of holding the address of an int star. Yeah? Looks weird, but that's how that works. So P is capable of holding, like its type is int star. Let me draw that down here. Its type is int star. It's capable of holding the address of an int star. All right, bless you. And now, that's perfect because I'm going to put an int star in there. All right, I'm putting the address of an int star in there because that's what new int star is going to do for me, isn't it? So if I say new int star, just like I said new int, I'm getting something of that exact type made for me on the heap, and I'm getting back a pointer to it, so another star has been added. That's what new tells me. It's living there. You need to hold its address, so you need to add a star into that type. So, all right, and if I say new int star, then I am making a box, shiny and new, on the heap that can hold an int star. Int star, that's its type. It's capable of holding an int star and has an address. It's like 100 is the address of that int star that we just made. So that's what P holds, the address of the int star. That's why its type is int star. All right, are we following me so far? This is weird. What can go in an int star is the address of an int. Okay, that's what we have to put in there if we're ever going to fill it with something normal. So let's do that. That's what this line does. So star P equals a new int. So we can read it right to left. Like the very first thing that happens is a new int. We know what that means. That was the previous slide. So that makes a brand new box on the heap capable of holding a single int. And it itself has an address, 104. And where am I shoving that address 104? Because that's what new int gives me back, right? It tells me where it lived. I'm putting that into star P. So star P is not here, that's just P. Star P follows it and gets me to this box. So I'm setting this box with 104, which is the address of the int. The type of that thing is a pointer to an int or an int star. They align. It's working. You see that? So that's going to hold 104. Bam. That's what the second line does. Are there questions about that? Do you see it?
I think it's a 104.
This?
Yeah, I think it's a 104.
Well, first of all, I'm just making up addresses. It could have been something different. But that's this. I am setting star P equals new int. Star P is follow P to get to here. So I'm setting this box. And then new int is whatever the address of this int that I just made, which I have made up to be 104. That's why 104 goes there. Okay. All right, ready for the last one? I think you can imagine what's about to happen. There are only 3 boxes, though. Only 3 boxes. Star star P equals 42. All right, 1 star on P gets me to here. All right, that's looking at 104. But that's an int star. I can follow that again. I can dereference when I'm at there. So dereferencing it once more, another star gets me to this box. And if I want to set that, that's now I'm going to set it to something. I'm setting it to 42, a normal int. So the types again align. Okay. Where did I? There. So that's going to go to 42, and that is going to be the original state of memory after those 3 lines have run. Are there any questions about that? Do we see it now? We didn't get it that way. It's a great example to like cover up my answer when I give you these slides. Try it again. All right, make sure you understood it. It's a little complicated, but it's useful. Useful knowledge, all right? And then delete P. If I were to say delete P, I'll use like green again, green now to show what happens if I were to do that line. Delete P. What? I guess there's a couple options, right? What could have happened? Would any brave soul like to tell me what they think will happen? What their idea is? It's okay if we're shy. You have an idea? What's that? No. It's allowable. What will happen is okay. It's okay to do this. It's not undefined. But now I have to go back to here. Like, what happens when I say delete I, delete R? Like, delete I here just says, well, I holds an address, right? That's how delete kind of works. The thing we're deleting is something that is on the stack. It holds an address. Essentially, I'm going to that address and getting rid of that memory. That's what delete does. So with that in mind, if I were to say delete P, it goes to P and it's like, all right, P holds address 100. I'm going to delete the thing in address 100. So this is what delete P does. It's just floating around, yeah. So that's called a memory leak. We've heard that before. I have now no way of getting to this 42. The only way was along this chain, and I just cut the chain. See that? Disgusting. So you don't want to do it in this order, first of all, but this is what happens. It does not just automatically get rid of this 42 for you if you say delete P, because it's really just going to that one address and deleting that one thing, and now I can never go to address 100 again because that memory has been reclaimed. Now, if I were to go to P to try to delete the 42 somehow, like that would now become undefined behavior. That would be weird. Okay? Does that make sense? Delete is only something that deletes heap things. Delete just works on the heap only. Stack memory lives as long as the function call lives. So like once the function call goes away, then your stack memory goes away. You don't really have any control otherwise. Okay? Yeah. But heap stuff, we have that fine-grained control with new and delete. Yeah. Other questions? These are good. Keep them coming. If you were to delete this 42, what would I say? Delete what? Before I did this, I can't do that one first. What would I put here to delete the 42? What do we think? I think I heard it. Other thoughts? Yeah. RP? Yeah. What do you think?
So for every new, do you need one delete?
Yeah, you do. There should always be a corresponding delete. Otherwise, they're mismatched. That's a great way to think about it. So delete, you guys said it. It's going to be, how do I get to here? Get to this box? Well, I need its address, essentially. That's what delete takes. It's going to take the address somehow. So I need the address 104, which is living right here, which is star P, before I deleted that. Okay. So it's star P. So that's what I should have said first. Delete star P. would go, before this X got drawn, it would go and get the 104 out and like, okay, I'm going to go to address 104 and delete that. Question?
Can you delete P with brackets? Would that work? Because it's printed.
No, delete bracket P. Yes, it wouldn't. It wouldn't work because this could have been address 204. They didn't have to be contiguous. The heap is just going to give you something wherever it finds space. It's not going to keep track that there was a chain of things. It's a good question, though. If only, right? Other thoughts, questions? All right. So yeah, great slide to come back to. It's a complicated question. I did not expect us to get it right, but now we know it. Hopefully, we see the importance. And the reason I'm saying all this right now is because we've used vectors, we've used strings, we've pushed back, we've done cool stuff, and we've essentially been letting heap stuff happen like this the whole time. And now I need to tell you the secrets. All right, so this is one of the secrets. Secretly, vectors are making and keeping track of a dynamic array, an array on the heap for you. If you push back and that array that was there inside of that vector secretly was not big enough, it'll just like make a new vector, put all the old stuff in it and make it bigger. That's how it's going to work. Same with strings. It's essentially a string is just a special case of an array of characters. A vector of characters. So yeah, that's a reason to understand this stuff and want to learn it. And I'm going to teach you how to build your own vectors soon. All right, that's where we're going. We're going to make our own. I hope we're ready. So I'm about to switch to something completely different. Are there any questions about any of the code lower level stuff we just talked about? Before I switch gears to draw more pictures. All right, so I want to talk about just like high level. This is essentially what the class is about, algorithms and data structures. Let's figure it all out together. Are we getting through all this? No, we're getting through that much today. So, okay. Let's learn these words. We probably heard them before. We probably know at least a little bit of the definitions. So, an algorithm, right, is just a recipe. It's just some sequence of steps to do something, to solve a problem for us as computer scientists, or like perform a calculation, but it could have just as easily been to bake a cake. Like that could technically be an algorithm, okay? So an algorithm is just a sequence of steps to do something, and we really care about having good algorithms in this class. And so we care about measuring how complex our algorithms are computationally. All right. So this term, computational complexity, refers to how much resources are being used by our program. So complexity is a key idea, and there's different ways to measure complexity. There's usually trade-offs involved with all the different ways that you can measure things, such as life, right? The two ones that we care the most about in class is how much memory are we going to use when we run our algorithm? Space complexity, that's what that's called. And then also how much time is it going to take to run this algorithm? Time complexity. Makes sense to want to care about those, I hope. And so that's because all those are finite, right? We only have so much memory to do our work with. Costs a lot to buy more RAM these days, right? And then we also only have so much time to wait for our programs to finish. Like, we need this answer back to the user within a minute or something like that. That's always at the backbone of everything we're doing. So, like, our lives are only finite amounts of time, right? So we care about computational complexity measured in space and time. There are other things that you could measure, but we will care about those for this class, okay? And so just in general, we care about the efficiency of our algorithms, and we're going to quantify that efficiency by coming up with numbers that represent how complex our algorithms are, both in terms of space and in terms of time. So that's where we're going, all right? I hope that makes sense. A little philosophical, which is cool to think about. And then to get there, like, how do we make things better? We're going to learn about cool ways to structure data. So data structures are just like ways of organizing the memory deep down inside of our program, understanding what these pretty pictures look like, right, deep down, and coming up with the right pictures for the problem, all right? So a data structure is a way of organizing, storing, performing operations on data. And when you hear the word data structure, you think about these kinds of pictures. Like, I know exactly, I could draw this picture for you if I knew about this data structure in full, all right? So you know exactly what the memory looks like arrays, for example. Arrays, things on the heap, those are data structures. An array is a data structure. So I know exactly, if you give me the starting address of that array and its size, I can draw a picture for you. I can tell you exactly what the address of every single index is in that array. That's what a data structure is. I know exactly, I can draw the picture, all right? That contrasts with the idea of an abstract data type, which you'll be reading about in your book if you have not already, which is like a higher level idea to a data structure. They do go hand in hand, though. An abstract data type, or an ADT, is when we're talking about the idea of something. So it's still like a type. It's still like a class that you could use, like vector, string, or something. It's defined, though, not by like the picture of what memory looks like, but by the operations that you could do to it. So it's a philosophical difference there. So with a data structure, like I can draw a picture of what it looks like in memory. With an abstract data type, I have options of implementations. I could implement it however I want to. It could just be a black box to me. I don't even know. But as long as it responds to your commands in the way that you understand, as long as it has the operations that particular ADT was supposed to have, then you're set. So, for example, remember the time before this slide, before I told you that, before you knew that vectors were secretly dynamically allocated arrays, a vector to you was just a black box, wasn't it? It was just like, all right, a vector is something I can make, and I can push back to it, and I can go to the dot add of the indices where I push back to. And as long as it plays that game properly, we don't even care if it's an array deep down, do we? It's like it could be some weird string that's holding all those elements, as long as it converts them back to ints when I use dot add, right? So the implementation didn't matter for vectors. It's just like how I used it mattered. That's going to be the difference, all right? I'll give more examples, but that's the secret, all right? So when we make data structures, usually the idea was that we have some idea of what we want to do. We have a list of operations, we have an abstract data type, and we're going to choose the data structure to implement that abstract data type and make it concrete in the most efficient way possible. That's where we're going, all right? So it's okay if that didn't make sense, but like that's the high level idea of what's going to happen in this class. So when you make ADTs, you come up with some operations that you want to do, like I want to do these things. Usually the words involved, you'll see a lot. It's like, all right, I want to access something. I want to go to an index. I want to update the value somewhere. I want to search for something that maybe has been placed within this idea of a data type. I want to insert some new idea rather than updating it. Those could be separate things. I want to remove something that I placed in there. Like think about how you'd remove something from a vector. Like, is there a dot erase? There is. How does it do it? I think at least there is for strings, right? So that's kind of where we're going. Data structure is something concrete. Abstract data type is abstract. It's in the name. It's defined in terms of its operations. Any questions before I show you more examples of that? I need to get more words and pictures out for you to fully understand it, I think. All right. So, yeah. So data structures, all about what memory looks like. You can draw a picture if you wanted to. It's concrete, all right? So data structures implement ADTs. ADTs are implemented by data structures. That's kind of how you think about it. So you know what's going on, for example, in an array. If I told you that there's an array called R of size 3, it starts at address 100, you could draw this exact picture, couldn't you? That's what it means to know about a data structure. All right, that's how it could be arranged in memory. I know exactly how fast it is. Like I can go to these indexes really quick because I can go to R of 1, R of 2, R of 0. Like that's all accessible to me. All right, that's what a data structure looks like. But an ADT looks like this, like a vector. That's what it looked like to us before I told you what's going on. Now we know that if I make a vector called vec or something, it's really got some big long, I don't know, array deep down inside of it. But it didn't have to. Secretly, that's what's going on. Really, it's on the heap. But we didn't know before. We had no clue what was going on inside of a vector. It was just a black box to us as CSCI 40 students. So it's just like, all right, as long as it plays the game, right, of responding to our operations. It's like, all right, hey, vector, push back 42 to yourself. And it's like, that's a void method. It's like, sure. And then as long as when you say dot at of that index that you just put it in, maybe it was index 3 or something, I don't know. As long as you get back the 42 that you just put in, then it is a vector, right? That's what it means to be a vector. It's playing this game properly of responding to your commands. So for all you know, that vector, and it's still a vector if this was true, it could have been implemented as just like some weird looking string, right? Maybe didn't have to be an array. Maybe it was like some weird looking string that held all of your elements. Could have been like 1 with commas to separate them. 1, 2, 3, 42 or something. Maybe that's what it looks like now. And it knows to get to index 3 by like looking for 3 commas and getting the int out with maybe a string stream or something. Like that could be a vector. Does that make sense? Yeah. That could be the implementation, even though it's ugly. It probably should use an array, but It's still a vector if you did it like that. The implementation is meaningless. The operations they reign supreme here. Okay, that's what it means to be an ADT. It's abstract. As long as it responds to your commands, it's correct. All right, so this is very philosophical. That's the idea. So the idea of it is a vector, not because it has an array inside of it, but because it responds to pushback and at and size and all those things that vectors should do. Okay, you could make it a string. You could use a linked list if you read about that in CSCI 40, like I force my students to. You could have used a linked list to implement a vector, but it would have been inefficient. You could do anything as long as it responded to all of those commands properly. The data structure that implements an ADT does not matter whatsoever. It matters to us in CSCI 41 because we care about speed, but pretend this was 40 still or something, all right? All that it means to be a vector is that it has pushback, it has at, it has size, and it plays those games properly. It doesn't give you something that you wouldn't expect, okay? What's under the hood does not matter at all right? That's the difference. Again, still, ADTs are implemented by data structures. Data structures implement ADTs, but one's concrete, one you can draw the memory of, one is just a list of ideas, of operations. It's higher level, all right? So, yeah, it implements it. I think that's what I wanted to say. So, just like that famous picture there. Does that make enough sense? Is it sinking in a little bit? It's weird. Just shout out if you have any questions about this stuff. It is odd, I know. But, yeah. I guess the key, like I've been trying to say, an abstract data type is implemented using a data structure. You've made a choice at that point to make it concrete. Those are the choices we're going to care about making. All right? So next, I have a question for you. You guys can get into groups, and why not? Please humor me. I'm gonna stop attendance after a couple minutes, so make sure you've done that if you haven't. But I would like you, please, to, as a group, you can elect a leader. Go to the written ice page, please. I'm going to delete it, clear it all out. I don't think there's much in it. But you can go to this create post, pick a leader of your group, and you can answer in and click submit. And that way I can see what you're thinking. I think that would be helpful. All right. What I'd like you to do is, as a group, with the people sitting next to you, say hi again, come up with a definition for an ADT, an abstract data type, all right, for a bank account. All right, to represent your bank account, just write down a list of all the things that a bank account should have. Bank account. How do I want to be able to interact with a bank account? Like method name 1, method name 2, those ideas. It's kind of like a class implementation. It's kind of like a class declaration, but without any member variables yet. Does that kind of make sense? That's what I want. What operations should you have in your list for a bank account? And then once you have that, start thinking about, all right, what kind of data structures could I use? Vector counts, an array counts, just like a single int is a data structure technically, a single double is a data structure technically. Like concrete things that you can draw memory diagrams of. What would you use of those to implement your bank account? How would you do it? All right, I'll use a double over here. I'll use an array of booleans over here. Why not? But yeah, try to get as fancy as you can. All right, make some operations that deal with credit cards, that deal with loans. How would you store those things? Think about that kind of stuff. All right, I think that's what I wanted to say. Does the question make sense? It's design an ADT in the way that you know how, and try to type your ideas up as much as you can. All right, it would be a good discussion, I think. Ready? All right, break.
Do we turn in one per group or one?
Oh yeah, you can elect a leader so you don't have to type it twice. That would be easier for you guys. But I'd like to see what you're thinking. I'll give you another few minutes.
For the name of the person.
Good question.
So start abstract, then make it concrete.
Investing, so it's probably
I know the class has storage and automations for that. For that update.
Or get.
Sorry, little Mike.
Well, much but shows balance. Show balance. So like happy use and show check they have show balance or like go check. I don't know that.
I don't use it. I don't use a credit card. I use
Voice cards.
The function is that it tracks the current updates it. Oh, yeah, like on some. You can do like for some credit cards you can do like an automatic payment. So like something that iterates over.
So I lost my card. I didn't check it. So
Yeah, something that iterates over.
oh, I mean, other than about what they use here. I know. Yeah.
Another couple minutes.
Are we talking about some music show or some basic? Because we're trying to put things for you, then we should have something that.
A lot of getters and sweaters or
Yeah, because then I would have to add.
for that extra.
Like, oh, I have many. I would. I would have seen. She doesn't say anything high school things, so I guess she's.
Yeah.
Something where the
Balance. Positive.
Yeah.
Or strong.
Maximum.
Yeah, it cuts more.
Are we writing this from the view of the user or from the bank?
I'd say just the programmer, whoever is designing this software. So it could be the bank in that case. Question?
So it's just like an ATM or it's like the idea of the bank account.
The idea of a bank account. It's abstract. Give you guys another minute to get something down and in there, okay? Press that submit button. Then we'll talk about it.
Yeah, I
Oh,
know.
we're gonna stop it.
Yeah.
No.
That case is the one that I talked about. Yeah. Well, once we reach the maximum. Yeah, but also like if somebody steals your credit card. Oh, yeah. All the bank, no, I think it's so you can't use the card. If somebody's got credit, buy stuff, buy what. And same with debit card. It basically just be a carbon copy of credit card. Oh, and that's like this. Well, yeah.
How's it draw?
Update.
All right, that's my timer. Take a few more seconds to finish that thought and click submit, and then we'll take a look. I'm excited to see.
Like, yeah, credit score. Interest. Saving. Yeah. And then if we will add on withdraw, yeah.
All right, let's take a look. Let us see. View. Oh yeah, so we got stuff for loans, credit cards. Like, think about the operations though. Like in terms of the operation, like all right, getters and setters, like give me the credit cards, give me the balance of the credit card, something like that. Yeah, this looks pretty good. Grape 6, I like it. Want to deposit, withdraw, do some cool stuff. All right, thinking about a linked list maybe for like all the transactions, something like that. That would make sense to me. Cool. I like that. So like, give me the name, give me the date of birth. Yeah, a lot of getters set new balance after you make some either withdrawals or deposits. That could be used to implement both, right? Cool. Give me checking, give me savings, give me the balance. Yeah, I like these. Very good. This is what I want to see. I like it. Balance, transaction history. You could store that as a vector because you could go in order of like, all right, this transaction came before that transaction, stuff like that, to make sure you didn't use too much of your money before you got paid. Stuff like that looks good. Add, remove, transfer, freeze account, lock account. Awesome. Interest. Yeah, you got to apply interest every month or however often it is. Cool. These look good. So yeah, we're thinking about the operations, like what do I want to do to these things? And then some of us have also thought about how would I store this data? It's like, it's a string. Give me the current balance, not as a double. Actually, they do store your bank account balance never as a double because doubles are imprecise. They're going to store your balance as an int in terms of cents. That will never be imprecise. So there's that to think about. So good. I hope that made sense. I think I can stop this now, like I said. Thank you for that. So yeah, we've got a lot of cool ideas. Let me just write a few that I can think about. Like, what do I want to do with a bank account? What are my operations? I would like to be able to deposit. That's a method. I want to be able to transfer money between my accounts. I want to be able to withdraw money from I'd be running that method on when I go to the ATM or something. Withdraw. I want to be able to see my balance, get balance, stuff like that. Boop. And then like apply the interest. That was a good idea. Every month or so. All those 50 cents or whatever. So, and now the question is, all right, every time I make a bank account object, what's going to be used to store this stuff? You have a name of the account, and that would be a string. Your current balance would be stored not as a double, but as an int. The rate of the interest, you'll have to save that somewhere because maybe different accounts have different interest rates depending on maybe how much money you have. It's interesting like that. And then like a bunch of like your history, right? A vector of, I don't know, transactions, whatever that type needs to be. That can be your bank account history, or like all the transactions you had for your checking account or something. I don't know. But yeah, you see the difference, right? It's like the idea is what I want to be able to do and then how I want to be able to make that all work out. Okay? That's what it means to implement these types, these abstract data types. Questions about that? Fun little exercise, I think. Yeah, so I guess all I want to do next, there's just a few slides left. I want to introduce you to your next lab, all right? I'm going to teach you how to make a vector, all right? We're going to make vectors from scratch for your next lab, all right? I'll give it to you next time. But I want to start off the implementation, and like most things from now on in this class, I am not going to write code. I'm going to draw pictures, pretty little pictures, and you are going to turn those pictures into code. That is what you're going to get very good at in this class. Okay, so there is a vector ADT. Let's think about that. It's essentially what you see when you go to like the vector library. It's like, oh, what do I have there? Why is that? There. Better on my eyes. It's a container. It's a vector. It's essentially these ideas. Like these are your methods, like size, .at, pushback. Those are, it's a fancier ADT, but let's make it simple. All right, so let's say that this is what I want to be able to do to a vector. This is what a vector means to me. I would like to be able to push back a value of a certain type. And what does that mean, right? That adds one element to the end of our vector, this idea of our vector, and it increases the total size of it by 1. That's always changing, right? And then the size, there should be a size method. That's another operation in our ADT that should give back the current size of my vector. If I push back 3 things, the size should be 3, right? .at, my vector's at method should give me back the element at a certain index, because vectors are supposed to represent contiguous memory in some way, something like that. And yeah, the idea of a vector is when you build one, like the constructor or whatever, it should start out empty, but it should have room to hold one thing. But that's arbitrary. This is now getting into like data structure-y concrete things. So maybe there should be a line here. The ADT is above. Now we're starting to get into concrete stuff. But secretly deep down, what's going to happen every time you make a vector, it's going to look a little bit like this. Once we make it concrete, there's going to be a heap array. Deep down, there's going to be an array on the heap. And when we start our vector, the constructor or whatever, it's going to make an array of just one element. It's room to hold just one thing at the start. So, because usually when you make a vector, you're going to put something in it, right? So at least have room for one thing. And then we'll have some other variables to keep track of like our size or whatever, stuff like that. But like the first line of your constructor is like the array member variable equals a new int on the heap, array of size just 1, something like that. It's silly to make an array of size 1, but it's a good example of something you can do. All right. So that's the start. That's going to be the vector. All right. And we're going to use these arrays. We're going to use heap arrays to keep track of what's in our vector. It's secretly going to be an array deep down, and that's where we're going to go when we do .out. Go into the heap array. Okay. So here's some more words now. So when we have a vector and a current array on the heap where we're storing our stuff, it is very possible that I would like to put 2 things in my vector, right? I have room for 1 right now if I make size 1 array on the heap. But the second I want to push back that second thing, something needs to happen, right? And that's the special sauce of a vector. So the idea for that is like, all right, if our current heap array is not long enough, we better expand it, all right? That's the secret. So I'm not going to give you code. I'm going to give you pretty pictures. So here's what's going to happen. Every time you have a, let's see, how do I want to do this? Every time you have a vector, here are going to be what your member variables look like. And then here's going to be what the heap looks like. Boop. So we're going to have, inside of all of our vectors, we're going to have 3 member variables, at least that I want to explain right now. We're going to have the array on the heap. All right. We're going to have the array on the heap. And maybe it has some room for some extra things. Like right now at the very start of time, like there's nothing on the array yet. There's nothing in the vector, but there's room to hold one thing. There's a concept of what's there and what we could hold. All right. So maybe the array has like 1, 2, and 3 in it right now, but there's room for one more thing. So like maybe that's what the heap array looks like right now. And then there's also some other things that we're going to need to store. The current capacity, total capacity of our heap array. Capacity. Right now that's 4. There's 4 things that I could have in this array, but I've only put 3 things so far. That's the size of the current array from the user's perspective. I'll call that num items. It's the number of actual things in that array, in the vector right now. So there's 3. Does this idea make sense? That's like the current state of this vector. The user's push back, let's say 1, 2, and 3. I've got room for 4 things. The user doesn't need to know that. They're never gonna. But that just means that I could push back one more thing and not have to change the size of my heap array. Questions about that? This is now implementation details. Now we're thinking about data structures. Does that make enough sense? So yeah, that's what could happen. That's what's going on. All right. So we're going to save the elements in the array on the heap in order. There might be some extra space there though. And then we've got a bunch of member variables. They're all private. The user doesn't get to see them. We've got our array that's holding the contents of the vector plus some extra space maybe. We'll always need some extra space to add more things. We'll have the current size of our vector, how big it is from the user's perspective, how many things they've pushed back. So that's what we give back when we ask for the size. And then the current capacity of our underlying heap array that may have more room for extra things. Okay? That's what it's going to look like. That's the standard way of implementing a vector. All right? And so when you make a vector, the constructor is meant to do kind of this. Let me draw it in more detail. Let's say I'm going to make a vector v2, and the constructor gets called right now to make it empty with room for one thing. What does that mean in terms of these member variables? I've got a capacity, a num items, and an actual array. I said that we're going to make this heap array of size 1 at the start, capable of holding one thing, but the vector itself is empty, yes? At the start of time. So from the user's perspective, there is nothing in this vector, 0 items. But for us, the implementers, it has the capacity to hold one thing right now. You see the difference there? The user never gets to see capacity. They don't need to care about that at all. That's just for us. Okay? That's how that works. That's what the constructor should do. Initialize num items to 0, capacity to 1, and make an array of that size, of whatever capacity size is right now. You can just keep on using that. This capacity is set to 1. That'll work. It's like new r in brackets capacity. That will work once you set capacity first. Does the constructor make sense? You think you could implement it? So that's what I'm going to be asking you to do. So these types, I think you can imagine capacities in it, num items in it, and an array is r is an int star if we're going to hold a bunch of ints on in our vector. If it's just going to be a vector of ints only, r would be an int star because it's going to be pointing to the start of a heap int array. All right, so all the stuff we got to have in our mind. So yeah, let's think about some of these implementations, and then I'll leave you wanting more by the time we get back on Thursday. So okay, .at. How would we implement this? All right. The idea of a .at for a vector is we want to go to that index of the vector. In theory, you could mess up, right? If the index is wrong, like you get index 42 of a size 5 vector, bad things should happen. But let's say they did it right. Then you should have an index to go to in your underlying heap array, shouldn't you? So let's see here. How do I want to say this? Let's say this. Let's say I've got this vector. We know this is how we're going to implement it. We've got a capacity. We've got a num items. And then we've got an actual array on the heap that we're pointing to. Dynamic array. And let's say the capacity is 3 right now, and the num items is, let's say it's 1. Yeah. So I've got something on the heap. I've got an array always of capacity size. That's how many things I could put in there potentially on the heap right now. But I've only filled in one actual element. Let's say that is what I've done. So I've got 1, maybe the number 1 right there, and then garbage here, and then garbage here. So from the user's perspective, the size of this vector is 1. Does that make sense? But let's say that's what it looks like. And then I go and I mess with, I don't know, if I ask for v at 0, it should give back the 1, right? How can you implement that? Well, it's just like, here's the array, go to it, go to that index. You see how that's not horrible? Assuming that index exists, you could have more complicated things. You could throw an exception if it didn't, like, that's what the vector library actually does. But this is what we could do, just let it go there. Let it crash if it doesn't hit the right index. But that's the thing that you could do. And also though, .at, you should be allowed to like use it for printing, but you should also be allowed to use it for changing. We've used that for vectors, right? V at 0. Psych, it's not 1 anymore, let's make it 2. Like you can do that. You should be allowed to use that same method to change things. So the type now of the .at method for us implementers is it should not give back just a copy of the thing that was there. We need to have it be allowed to be on the left side of an assignment. So it needs to give back that thing for setting purposes. And the way you do that is you give back a reference to it. So the type of .at is not int at, and you give it the index for this method, int index. Like you might imagine it could be, because I want to do this. So I need to give back an int reference. That will allow me to do it like that. Because if it gave back a reference to that int, I can put it on this side, and then I can make that actual change happen. All right, so that's a weird thing to put a reference and a return type. You'll get more and more used to that as we do it. But that's the correct type for the at method, at least in C++. Any questions about that? It's a little weird, a little philosophical. It'll make more sense when you do it, but like, do you see how you could make it work? At least for the getting part. It's like, how do I get that thing? Just like go into R at that index. The index that I was given. You can implement vectors. You're gonna. All right, and then size is even easier, right? If you have a vector that you've been building up, size is just a getter. It's just like, what is the size of this vector? How many things have been placed into it from the user's perspective? That's what num items is keeping track of. That's what we're doing every time we either add one to num items when we push back or stuff like that. All right, so num items is always keeping track of what's actually in this vector from the user's perspective. We're kind of tricking them, right? Because from their perspective, if this is what memory looks like, the user thinks there's only one thing in this array. I can't go to index, I can only go to index 0. I can only do .at 0. I can't go to .at 1 or .at 2. But really, that wouldn't be an error. You just get garbage, and you could set the garbage, I guess. It would be undefined behavior, I would say. From the user's perspective, it would be a bad idea. But really, that array, deep down, is capable of holding other things. And that trick gives us vectors, kind of. But yeah, dot size is just like how many things are in that vector from the user's perspective. So this is all an illusion to them. It's a black box. They don't get to care. That's our job to care. Okay? So size is easy. It's just like whatever num items is. That's how many things have been placed into that vector so far. Does that make sense? And you can imagine pushback is going to increment num items. That's what that does. Pushback is the complicated one. There's two thoughts, right? Because either it's easy and there's room for something. Like I can push back here right now. I just go to the next index. It's fine. But if there's not room, then it's a bad day. Okay, so there's two cases. This one's the hard one because you might run out of space. Okay, let's say I have this vector. Boop. I'll have to draw a little small. And I've got a capacity, I've got a num items, I've got an array on the heap. I'll say cap num items, I've got my array. Let's say that the capacity initially is 2, the num items is 1, and the array on the heap is this guy. So I've placed one thing on that heap so far. Maybe it's the number 1, then there's garbage there. So let's say that is the current state of memory. And I said v.pushback of like 2. This is not horrible, right? Because there's room. The capacity exceeds our num items. Yeah, that would be the check. There needs to be an if statement right now. If we have room, that the capacity is more than the num items, then I have empty space in that heap array still. I can safely put something there, and that's the end of the story. So if I could safely add one more thing, then do it. The implementation is going to be like, what index do I need to go to? This is 0, 1. It's going to check out that always you go to index num items, which is kind of cool to think about. That's always your open index. Go there and set the value to whatever you needed it to be. 2. And then always increment num items because you just added something else. That's always going to happen. So now it's 2 and 2. That's the current state of memory after I push back 2. Do you see it? That would not be a horrible implementation, but you got to make sure you can. You got to make sure you can. And now let's do the hard one. Let's say that, all right, now I say v.pushback 3. how do I fix this problem? Because, all right, now I know I have capacity equal to num items. I do not have room for the 3. There's no room for the 3. So here is how vectors get implemented. This is an implementation decision, but it's the right decision for speed and memory's sake. If you do not have the capacity to add anything else, you must make a new heap array. You cannot extend a current one. You must make a new one. And then you copy everything over into that new one. That new one should be bigger, all right? You could make it 1 bigger and copy everything over, and then you have room for that new thing. But that would, like, every time then you'd have to make a new heap array, copy everything over, right? So that's inefficient if you're just to make a 1 size bigger array, because maybe in a loop you're adding a bunch of things. You just keep on resizing, making new things on the heap. That would be disgusting. So what we've all decided to do, and mathematically this turns out to be the right answer, is we're going to make a new array on the heap with double our current capacity. That's going to be the right trade-off to make here, all right? A new array on the heap with double our current capacity, and then we'll copy everything over. So, all right, you try to push back 3. I don't have the room for that 3. I'm going to make a new array of size capacity times 2. So 4 things total now. And then I'm going to copy everything over. This is like a temporary variable right now. Don't overwrite R just yet, because like we still need the old one right now. Bring everybody over, the 1 and the 2. Now I have garbage here only. And then you're good to delete your old R and move in the new one. Does that make sense? You're going to need to do that. You need to turn those X's and arrows into code. And then you're pretty much home free, because now you have room, right? Once you've done all that, also capacity needs to be reset, because now it's size 4. But once you've done all that, it's essentially case 1 all over again. Now it's as if I were there, and now I have room, right? Then you apply all those other rules. It's like, okay, now I have room. I go to index num items. So this is 0, 1, 2. That's always going to be the next index, the next open index when you have one. Go to index num items, place the thing that I wanted to place there, 3, then increment num items. So now this is supposed to be a 4. 4 capacity, 3 items total. Does that make sense? You think you could implement that? I think you could, with enough thought. But that's pushback. That's the harder one. And again, I hope you can see the reason why we're going to double is so that we got some time to add more things, even if the user wanted not just 1 more thing, but like 2 more things later. I don't have to keep resizing. Because if you kept resizing and copying things over, that's inefficient. Just at a high level, I hope you can see that. So yeah, just let's see. One last example. Let's say I've filled this one up too, right? Let's watch it continue. And then that'll be it for the lecture part. So let's say I've got this vector. It's got a capacity. It's got a num items. And it's got my heap array always. Let's say I've got the, what have I done so far? 1, 2, 3. Let's say I've got the 1, 2, 3. Put room for a 4th thing. Boop. And so my num items is 3, my capacity is 4. And let's say I ran these 2 lines. Let's say v.pushback, I don't know, 42, and then v.pushback, some other number. Boop. 55 or something. There. So, okay, working on this one, 42. Well, this is case 1, right? This is, we can add 1 more thing. Our num items does not exceed our capacity, and it's not equal to it either. So we're set to go to that index num items of my array. So that's index 3. Go to index 3, place the new value there, my 42. I'll do this in green for all the new stuff. Place the 42 there. Then I've just added a new thing, so my num items must also increase. Okay? So now I did it. I added the 42 to my vector. Cool. And then, so that's case 1. That's the easy case. It's just like add the thing, increment num items when you can, when the capacity and the num items allow for that. And then you have the hard case sometimes. Okay? It's going to get less and less often because they're going to keep doubling the size, and that's kind of how the trade-off works. There's some cool math behind that you'll study one day. And, all right, so now I'm trying to add this 55. I do not have room. The capacity is 4, the num items is 4. It's impossible. So I need to resize. All right, so the steps are, I'm going to make a brand new array on the heap. of double my current capacity. So my capacity is 4. I'm going to make a size 8 array on the heap, capable of holding 8 things. And then I will copy over everything that was already in there. Don't delete it yet. 1, 2, 3, 42. And then I've got garbage after all that. And then I can get rid of the old one. Get rid of that old array. We don't need it anymore, right? So then I can chop off this pointer and have it point to that new thing that I just made on the heap, okay? And now I'm back in case 1 land after I increment capacity by double. So now capacity is 8. Does that make sense? Capacity is 8. There's 4 things in this heap array still. It's just a different place in memory now. It's still fine. And then the array has room. So now we're back in case 1 land where I can add something new. Perfect. Beautiful. So now I can run all those rules. Like, all right, 55, go to index num items right now. Index 4, that's the open index because I have room now, capacity versus num items. Add the 55, increment num items. There are 5 things in this vector. And the capacity is 8. So I could have 3 more pushbacks before I have to resize again. Yeah? And that's, I think, all I wanted to say about pushback. Are there any questions about this diagram? Oh, hello. I don't know what just happened. Are there any questions about that? So yeah, this is what you'll be coming back to when I give you the lab. You'll be taking these ideas and taking these pictures and implementing them, right? Making the abstract concrete. It's the beauty of it all. So yeah, I think that's all that I wanted to say for the day. Hopefully you learned some cool stuff, and we will come back next time and learn even more cool stuff. And then I'll also give you your lab 1, which that's going to be the vector lab. All right? So the rest of the time is all yours.